Hello everyone. This is Rakesh Samantra here, your chemistry tutor. So, today we are going to study a very important topic for NEET Chemistry as well as for JEE Chemistry, as well as those who are studying for 11th and 12th. So, this is basically electrophilic aromatic substitution in phenols. We'll be simultaneously using some textbook stuff from the NCERT, some popular textbook stuffs, as well as we'll be explaining it side by side. Basically, to begin with the basics, we all know how the structure of a phenol looks like. Okay, and this is the basic stuff that we have studied about phenols right from the beginning of maybe 11th. We all know this is the phenol, and we all know that it exists in the form of resonating structures. And basically, we know that it undergoes positive mesomeric effect. So this phenol lone pair, we know that it can delocalize here and this bond can go here. That we can write as another resonating structure. So basically you can write this as O, this is H, and this is positive since the electron pair has left from oxygen and now it's going towards the carbon. And this is a negative charge. So this is one of its forms, and it can also exist in another form where it can undergo a phenomenon called extended conjugation. So if you look at this, the extended conjugation phenomena will be drawing the same phenol but in a manner of extended conjugation. Extended conjugation means suppose this is the structure, this lone pair can go here, and instead of directly delocalizing at the ortho position, we know that this is called the ortho position. This bond can shift here, and this bond can further shift here to the carbon at the fourth position. So the final structure would look something like this. Basically, positive charge on oxygen, the conjugating structure will be formed something like this. So you see in both the cases, two particular sites are there where the electron density is increasing. One is this site, which is the ortho site, and one is this site, which we popularly call as the para position. Okay. So that is why in most of the aromatic substitution reactions, basically the electrophilic aromatic substitution reactions, we know electrophiles are what? Electrophiles are electron deficient species, which we normally write or generalize as E plus, which might be NO2 plus. It might be even a halogen in case of Friedel-Crafts reactions, or it could be CH3CO plus as well. Okay. So these are all the electrophiles which can be or we have generally studied in case of Friedel-Crafts alkylation or acylation or in case of nitration reactions. So you now see the reason why most of the electrophilic aromatic substitution in phenols usually they undergo either at the ortho position or the para position because the electron density is the maximum at these sites. Okay. So next we are now we know the basic phenomena. Now we know why these particular products are formed, why ortho and para positions are normally targeted by the electrophiles, because electrophiles are positively charged species and they look for high electron density sites. So they target the ortho positions and the para positions. So now we come back to some basic reactions which are normally mentioned in the NCERT textbook. So you see the first one which I just mentioned, it's the nitration reaction. Okay, the nitration reaction. So it says with dilute nitric acid at low temperatures as low as 298 Kelvin, phenol yields a mixture of ortho and para nitrophenols. This is what we just now studied. Why ortho and para positions are targeted. And this happens when it is provided with dilute HNO3. So we'll take a look at the basic mechanism as well, how NO2 positive is being formed basically, and we'll take a look at some of the basic reactions as well. Okay, so you see, this is the dilute HNO3. This is the nitration reaction. Okay, let's study about the nitration reactions. let's study about the nitration reactions. So what happens is they normally provide acidified like nitric acid. So basically nitric acid, we all know it is HNO3, right? So this is normally represented like this. So you have a hydroxyl unit here and you have the NO2 group here or nitro group here. Okay. So when you provide, so this is how you write HNO3. So when you provide a source of an acid in the solution, this oxygen has lone pairs, So this lone pair captures this proton, and simultaneously what you get is basically a positive charge on this particular oxygen. Okay. Simultaneously there is a positive charge on this particular oxygen. There will be another proton because OH was already there. It has absorbed this proton. Okay. So there is another hydroxyl unit here and the positive charge on the this oxygen unit. Now to neutralize this positive charge on the oxygen unit, this bond will come towards oxygen because oxygen has a positive charge. It's unstable in this state. So to neutralize it, it will move there. You get water, that is H2O. This part is H2O, which will leave. And basically, since this bond has been broken, now the nitrogen center or the NO2 group will be the positive charge containing group. So you get the NO2 plus nucleophile from here. And this is the electrophile in the case of nitration. Okay, this is the electrophile in case of nitration. So simultaneously, we already know that if we have a phenol ring here, and if there is an electrophile like NO2 plus here, we have just now seen that the ortho positions and the para positions are highly populated with the electron densities. So that is why you get two products. Basically, one is the ortho product and the other is the para product. Okay. Now you might ask which one is the major one. So I would like to mention that in most of the cases, this one is the major product because of a phenomenon called steric hindrance, basically. Because of the phenomenon called steric hindrance. Okay. So steric hindrance means that for steric reasons, bulkier groups like these, they start steric repulsions with the electron densities being side by side in the ortho position. So that's why they prefer to normally go at these particular positions. Okay, but and normally this happens, but there are some exceptional cases. We might come to them later. Okay, so this is all about, I think, the nitration part. So I think I've explained you the nitration part. Okay, so another very popular reaction now, we'll go through another electrophilic substitution reactions of phenols, after which I think you will be more clear and completely good to go with this concept. So next is, just a second. Okay. So we'll come to the next part. You see, the next part is this is another reaction which I wanted to talk about. So this halogenation. Okay. So this halogenation, there is a particular special thing about this halogenation. It says the usual halogenation of benzene takes place in the presence of a Lewis acid such as FeBr3, which polarizes the halogen molecule. But in case of phenol, the polarization of bromine molecule takes place even in the absence of Lewis acid due to the highly activating effect of OH group attached to the benzene ring. So as you can clearly see, if you use normal benzene instead of the phenol, so you require some, strong Lewis acid. Like normally we use FeBr3. Okay, normally we use FeBr3 as the Lewis acid because acids are proton donors and electron pair acceptors. So this is an electron pair acceptor. Okay, we normally use this, but since in case of phenol, it has the highly activating OH group, as we just now saw how easily it activated the electron density at ortho and para positions, you do not need an external acid to facilitate, the halogenation of this electrophilic bromine ion at the ortho and para positions. So the usual halogenation here, it does not need any Lewis acid. That's what it talks about. And another thing very important for these last two reactions which I'm going to explain to you, very important. First is when you treat phenol with bromine water, and when you treat phenol with normal bromine in carbon disulfide, suppose. So there are two types of solvents here. Okay, so if I talk about this, just a minute. Yeah, so there are two types of solvents here. One is, in one case you are trying to perform the bromination reaction in, suppose, water, that is bromine water. It's an aqueous solution of bromine, and in one case you are trying to carry out the reaction in case of a non-protic and a non-polar solvent like cesium, carbon disulfide. Sorry. So in both the cases, the influence of the solvent is seen here, where in this case, where there is a polar solvent, water is a polar and a protic solvent. Basically, polar because of the high electronegativity difference and the existing dipole moment. So water is a polar protic solvent. It has basically dipole moment, overall dipole moment, as well as there is an active proton which is attached to a highly electronegative oxygen. So we call the proton activated. So in such cases, the product which is formed is a tribromo product. Okay, the product which is formed is a tribromo product. This is basically like this, where you get it as tri-substituted product. We call it 2,4,6 tribromophenol. We call it 2,4,6 tribromophenol, and it gives you a white precipitate. Okay, it gives you a white precipitate. Whereas in the other case, where you are using carbon disulfide, carbon disulfide is kind of a non-polar solvent, because so basically the overall dipole moment is cancelled here, you see. So it's non-polar, okay, and it's non-polar solvent, and not only non-polar but aprotic. Aprotic means no active proton present here. Like in this case, we had a proton which was attached to oxygen, which is highly electronegative. No active proton here. So in this case, it was observed that you get the normal bromination products. That is your mixture of ortho bromophenol and a mixture of para bromophenol. Okay. So the main reason is the solvent here. Basically, here the protic solvent is there, and we know in presence of protic solvents like these can stabilize. So basically, what happens is, if I explain you in detail, in presence of aqueous medium like water, this phenol can undergo dissociation to exist in the form of a phenoxide ion. This is called a phenoxide ion. This is what you call a phenoxide ion. This phenoxide ion with a negative charge, you see there is a negative charge, and it is much more electron directing at the ortho and para positions compared to the normal neutral phenol. And this negative charge is also stabilized in the presence of the activated protons of the water molecules, suppose, like this. So this water molecules, or these we can say polar protic solvents, they stabilize the negatively charged phenoxide ions and help them to direct more electron density at the ortho and para positions, due to which they become more activated. Okay, so in this case, there is more activation at the ortho and para positions compared to this case because of the change of the solvent. So the solvent plays a very vital role here. So that's it. So I think I hope I cleared all your concepts, and we'll get back for more electrophilic aromatic substitution reactions. So keep studying, keep enjoying chemistry. Thank you. See you next time.